Hello everyone. In the earlier lectures, we have discussed about basic principle of NMR spectroscopy and some of the aspects of interpretation of NMR spectra. In today's lecture, we will talk about signal splitting and coupling constants in NMR spectroscopy. What you see in NMR spectra, generally you see single peaks, like if you look at this CS3, CS2, Cl ethyl chloride. We know that as per earlier lectures, there are two types of proton in this compound. So in proton NMR, you will see two peaks. For A type of proton, you will get a single peak like this. For methyl group, you will get another peak here. They look like a single peaks, but if you magnify them and if you look in high resolution spectra, in that case you will see that these peaks are not actually single. They are having splitting. They are multiple peaks. For example, this peak, if you magnify, you will see that it is split into three, so it's a triplet. And the another peak, if you see, this is actually is a quartet, split into four. So B peak is a triplet. There are three splitting, split into three different peaks. And A peak, A type of proton, they are a quartet, they are four. So this splitting gives more valuable information about number of neighborhood protons which are attached to the carbon atom, which is linked to the hydrogen atom having this peak under question. So these protons, because we know that protons do have a magnetic field because they are charged and they are also moving in a molecule. So as a result, they also create a magnetic field. And we understand that in NMR, the compound is kept under some external magnetic field, which is applied from outside. So these protons, which also have their own magnetic moment, their own magnetic field, they disturb each other's magnetic properties, and that's called splitting by protons. So the protons which are in neighborhood, they split each other's signal. Those protons, those are called coupled protons. For example, here these methyl, there are three protons which are giving this B type of peak. So this is split into three. This is split into three because in the neighborhood of these three protons, you have two methylene protons. So these two methylene proton, they split peak for the methyl proton and vice versa. And this splitting is defined by a rule called N+1 rule. So in N+1 rule, where N is the number of proton. For example, for the B methyl proton, so methyl protons are having these two methylene proton in the neighborhood. So as per N+1 rule, here splitting would be 2 + 1. So it will be a triplet, and that's what you see in a high resolution NMR spectra. Similarly, in case of A type of proton is split into a quartet, 4 peak. It means in the neighborhood there should be 3 protons, and those are actually there in the methyl group. So these protons which split each other's signal, they are known as coupled protons, and it's called multiplicity of the peaks. So actually the spectra, if you look at this compound, the A peak would be a quartet which is split into 4 different peaks, and B peak would be a triplet. So in H1 NMR spectra, the signal is splitted, and the splitting is defined by N+1 rule, where N is the number of equivalent protons bonded to the adjacent carbon atom. And these coupled protons, they split each other's signal. The number of peak in a signal is called multiplicity of the signal in a given NMR spectra. This splitting of the signal is caused by spin-spin coupling. So spin-spin coupling means the magnetic field of a neighborhood proton, they actually cause splitting of each other's signal in NMR spectroscopy. And the number of peak in a multiplet provide information about neighboring proton, because we know that Generally, the splitting is caused by n+1 rule. So just by looking at the number of peaks, we can say the number of protons present in the neighborhood of that peak. Splitting is caused by the interaction between unequivalent protons. So that's also known as coupling. So if you have unequivalent proton in the neighborhood, they cause splitting, and that splitting is defined by n+1 rule. And proton-proton coupling usually takes place 3 bonds away from each other. Means if you have a compound like this one is carbon atom, another carbon atom, you have hydrogen here and you have hydrogen here. So the distance between these two hydrogen atom is 1 sigma bond, another, and the third one. So in order to have splitting, the distance between two protons should be equivalent to 3 sigma bonds. And the number of peak or multiplicity comes from the number of proton interacting. So from the multiplicity of peak, number of protons which are splitting each other, which are in neighborhood 3 sigma bond away from each other, that number can be calculated. So for example, in this case, you see in ethyl chloride, the CH2 peak, the peak for the methylene proton is a quartet. Quartet, it simply means as per n+1 rule, there are 3 protons in the neighborhood. And similarly, the peak for methyl group is a triplet, that indicate there are 2 protons in the neighborhood of these methyl group. And in the intensity also varies. If you see in case of a triplet, the intensity is actually 1:2:1. This is the ratio of the intensity of the peak. Whereas for quartet, in this case, the intensity of the peaks which are splitted is 1:3:1. So you can see that on the y-axis. So now you look at this compound CH2Br and CH2F. So there are 2 types of protons, we know that, for each methylene group. And because you call them A and B types, so both an A and B types, they are having 2 protons in the neighborhood of each other. That's why n, the value of n would be 2 in both the cases. And as per the rule, the splitting of their peaks would be n+1, that's 3 in each case. So for this compound, you will get 2 peaks, and each peak would be a triplet. 2 different hydrogen neighbors don't follow n+1 rule. That's another rule for splitting. If the neighborhood protons are different types, they do splitting. They cause multiplicity, but the multiplicity does not follow n+1 rule. In fact, you get multiple peaks, and that's called multiplets. For example, this compound CH2F, CH2, CH2Cl. There are 3 types of proton defined by A, B, and C. In case of A and C, A is having 2 protons in the neighborhood, same C is also having 2 protons in the neighborhood. So for A and C, you will get a peak which are peaks which are triplets. They follow n+1 rule. Whereas in case of B proton, B is surrounded by A-type proton and C-type proton. So these 2 are different protons. So the peak splitting for B-type will not follow n+1 rule. You will get multiple peaks in that case. So those won't be simply 2+1 or 4+1. You will get many peaks corresponding to these B type of proton, and that is because of these are 2 different hydrogen atoms in the neighborhood. So that's another rule for splitting. So if you look at this compound ethyl benzene, so in ethyl benzene we know that there are 5 types of proton here, and all these protons, if you look at their splitting, A types, B types, C types, and E types, they follow n+1 rule because they are surrounded by same kind of protons from the neighborhood. But for the D type of protons, in both cases the neighborhood protons are different. You have C one side and E another side. So splitting of D also will not follow here the n+1 rule. In fact, you get multiple number of peaks in this case. And in case of this aromatic compound, these all the peaks C, D, and E, they lie between 6.5 to 8 ppm. and you get many peaks there which are accumulated on this value of frequency. So now look at the mechanism of splitting. So here we take another example of a 1,1-dichloroethane, CH3CH2Cl2. If you take NMR spectra of this compound, we know that there are two types of proton, one corresponding to methyl group and other one corresponding to the methine group, CH group here. So methyl group, there are 3 proton, CH group, there is single proton. So peak for methyl group would be a doublet, because you have 1 proton in the neighborhood of the methyl group protons, whereas in case of CH proton, it's a quartet. That's because there are 3 proton in the neighborhood of this proton. They are coming from the methyl group. Now let's see how do you get these quartet and doublet. So first we'll look at the splitting of methyl hydrogen atom in this compound. So this is methyl hydrogen atom, CH3. So these 3 protons are at equivalent position. So we understand by now that you will get a single peak from there. And if there is no other proton is in the neighborhood of this methyl, you will get a single peak like this. So this is the chemical shift of the signal of methyl proton if there were no proton on the adjacent carbon atom. But here you have a proton on the adjacent carbon atom, that's a CH proton. And this proton, we know that is also has a magnetic field. And in NMR, we also understand the compound is kept under a fixed magnetic field, applied magnetic field that has a direction. So let's consider this is the direction of applied magnetic field from outside where compound is kept under. And in this case, the methine proton, the CH proton, the single proton. So this proton is also having its own magnetic field. So the magnetic field, the magnetic moment of this CH proton has 2 possibilities. Either it can align itself in the same direction as of the applied magnetic field or in the opposite direction. So in both the cases, it will influence absorption property of methyl protons. So if the magnetic field of the methine proton is in the same direction as the applied magnetic field, it will add to the applied magnetic field, because we know that if outside magnetic field we say it's X, the value is X which we are applying from outside, and the proton, the single proton from CH group, if it is aligned in the same direction, its magnetic field is also aligned in the same direction. So and that value is say A. A is the magnetic field created by CH proton. So the net magnetic field felt by the CS3 proton would be A plus X. Means additional magnetic field would be felt by CS3 protons. So in this case, this compound, the CS3 proton would absorb high frequency, high energy radiation in order to resonate, that we have discussed in the earlier lecture in basic principle of NMR. So that means you will get a 1 peak at high ppm, high frequency, more downfield. Why? Because this proton, CS3 proton, they are feeling extra magnetic field which is applied from outside, is additive. Magnetic field is a vector quantity, and if the magnetic field of the CH proton is in the same direction of the applied magnetic field, it means CH3 proton will have additive effect. They will feel more magnetic field, and that's why it will absorb high frequency in order to resonate. So you get a peak here. So this peak represent when the methine proton magnetic moment is aligned in the same direction as of the magnetic field applied in the NMR machine. The second possibility is that this vector, this magnetic moment of CH proton may be aligning into the negative side, I mean other side, opposite side of the applied magnetic field. In that case, the magnetic field felt by CS3 proton would be X minus A, where X is the applied magnetic field and A is the magnetic field created by the proton, and that's also oriented in opposite direction of the applied magnetic field. It means the net magnetic field felt by CS3 proton in this situation would be little less. slightly less, and hence it will absorb lesser frequency in order to resonate in NMR spectroscopy. And you get another peak here which is slightly off field. The difference is very little between them. So you get two peak is a doublet, and the reason of the doublet is alignment of the magnetic moment of the neighborhood proton. So if the magnetic field of the methane proton is lined up against the applied magnetic field, it will subtract from the applied magnetic field. So the adjacent methyl proton will show a signal at a slightly lower frequency, this one. So that's why you will get a doublet in case of CS3 proton in this compound. Now let's look at the splitting of this methane hydrogen atom in the compound. The methane hydrogen atom, it is surrounded by these three hydrogen atoms. So in this case, the three hydrogen atom will influence the magnetic property of this CH proton. And these three hydrogen atom, if you call them say A, B or C, so these A, B, C, they have variable possibilities of their orientation of their magnetic moment. So for example, if A, B, C, three proton of methyl group, they are aligned in the same direction as of applied magnetic field, which we call, say this is going upside on the page, the value is called X. So in that case, the CH proton would feel the magnetic field that is X plus A plus B plus C, means additional very high magnetic field, relatively high magnetic field would be felt by CH proton. So in that case, when it's aligned in the same direction, so due to extra magnetic field felt by the CH proton, you will get a peak which is slightly off field, means it will absorb slightly higher frequency in order to resonate, and the peak is this one. So this is the situation when you feel the proton, CH proton, feel maximum magnetic field. In the second possibility, that out of these three proton, two protons are lined up in the same direction as of applied magnetic field and one proton in opposite. So in that case, the CH proton would feel little less magnetic field, and in fact here there are further probabilities that A and B may be facing in the same direction, C in the down, or A and C would be facing up, B may be down, or BC, both BC may be facing up and A going down. So there are three possibilities in this case. Hence the peak height, the intensity of peak would be 3 times more than the first one. So that situation is represented by another peak here. So you'll get a peak slightly upfield. Here the proton would absorb slightly lesser frequency in order to come into resonance. Then the third possibility is that out of 3 methyl proton, any two proton are facing downside opposite to the applied magnetic field. One proton is showing additive effect. It's lined up in the same direction as of applied magnetic field, and that also again would have 3 combinations. So that's why you get another peak here, which is also 3 times of the first peak, which is represented by these orientations of the methyl protons. And similarly, the another last possibility is that all the 3 protons of methyl group, they are lined up in the opposite to the applied magnetic field. So in that case, the net magnetic field felt would be X minus A plus B plus C. So that would be the least magnetic field felt by the CH proton when all the 3 protons of methyl group are lined up against the applied magnetic field. So in that case, the peak would be more and more upfield, and you get this another peak. And because there is only one possibility, that's why the peak height is also less. So the ratio here, it would be 1:3:1. So this ratio, peak height, is basically represented by possible combinations of orientation of hydrogen atoms in the neighborhood. So you get a quartet signal for the CH proton in this compound. Splitting is observed if the protons are separated by 3 sigma bond. This is another condition of splitting. If the protons are from 3 sigma bond away, like they are represented here, so they are 1, 2 and 3, only then they cause spin-spin coupling, they cause splitting of each other. If they are more than 3 sigma bond, like in this compound, they are too far, so they cannot split each other's signal. Or if they are more than 3 sigma bond, but one of the bond is a double bond or triple bond, they can still split each other's signal, and that is called long range coupling, like in this compound. But it will be interacting weakly because they are anyway distant, but because of presence of double or triple bond, they are the distance between two proton is shorter, so they still cause splitting. No splitting by equivalents. Equivalent proton, they do not split each other's signal, like in case of the CHF compound. These both protons are of same types. That's why you call them A-type proton. So you get a single peak in NMR spectra, and this single peak is not splitted because there is no proton in the neighborhood. They are same types. So N is 0 here. So the peak you get is singlet, a single peak without a split. So that's another rule in peak splitting. Multiplicity of signal and relative intensity also, they have a ratio, like in case of doublet. So both the peaks should have the same intensity, 1:1 ratio. If it's a triplet, the ratio would be 1:1. If it's a quartet, the ratio would be 1:3:1. Or if it's a quintet, the ratio would be 1:4:6:4:1. So the intensity would vary, and we have seen that the varying intensity depends on number of possible combinations, orientations of neighborhood proton, magnetic field of the neighborhood protons. And if you look at the difference between a quartet and a doublet of doublet, you also get peaks doublet of doublet in the NMR spectra, but doublet of doublets and quartet, they are different. How they are different? By looking at the intensity, the peak height, you can differentiate them. In a quartet, this is the peak ratio 1:3:1, whereas doublet of doublets, all the 4 peak would be of same height. The ratio would be 1:1:1:1:1:1. So key points from here: the peaks can be splitted due to neighboring different hydrogen atoms. Splitting is observed by 3 sigma bond distant nuclei. Peak is not splitted by equivalent nuclei. N+1 rule is not followed if the neighbors are different for a given proton.